All right, let's check our sound here. All that looks good. Should be pretty all right here. Okay, so we won't take too much time getting into it, but this is the Linux Systems Administration Unit 15 presented by me to the Professional Linux Users Group. We actually had a meeting yesterday. That's why the date says the 21st, but we're recording it today so that we can get all 16 of our courses recorded. So let's get into it, and we'll talk about what this week entails. So a little bit of housekeeping stuff. If you have questions, ask me them down in our Discord. This is our 15th class meeting. We've got Christmas this week, so obviously we're going a little lighter on some of the work. Plus, a lot of people have a lot of time to work on their projects, so I'll let people work on their projects a little bit more. But if I had any announcements or any reschedules, I'd put them here. Last week, we were talking heavily about inventory and Ansible. Like how does the tool Ansible work? How does automation work? It all starts with a good inventory. Then we learn how to use the tools individually as one-offs against different environments. Typically, I mean, you could jump right into playbooks, but ad hocs are a nice way to get into it. And then you start jumping into playbooks and understanding how tasks and roles work. Now, the focus of last week was implementing Ansible and putting it into your administrative work. It was not about learning how to use Ansible. We have all kinds of projects and labs and stuff for you guys to work on to learn Ansible. So last week was more about how it kind of works, and that's what the different questions were about. All right, last week you had a lab and then you had a project. You should be getting done with the project if you're doing the course. There's a lot of work to it, so obviously if we're almost near the end. And this project, this course is going to end on January 19th. So you can do anything you want up until there, but that's going to be the cutoff date, January 19th, midnight my time. No other submissions or whatever will be accepted as far as getting the cool little the cool little certificates that we're doing for this one. So, all right, this week we're going to talk about incident management, and there's some questions this week around Six Sigma and how that works for engineering type problems. And then we're going to talk about like visualizing and looking at data. So there's a couple of questions here that are going to pop up as discussion questions. Here, we'll go look at them real quick. The first discussion question is, your managers are all fired up about implementing some Six Sigma. You're the administrative, maybe you're on the network operations team and you're the lead, and you decide to go familiarize yourself with some of the topics so you can pass it along to your team. Some of the junior engineers are going to ask you about it, so you decide to go read up a little bit on the Six Sigma process, and you learn about cleaning up your environment. This could also go for like cleaning up your software, your code, your branches that you're using, those kind of things. So there's a lot to this 5S methodology that might help out, and it's good to understand. And then what are the layers of how we define a process? We're going to look a little bit at processes today and how when a process breaks, we can then go troubleshoot that process. So that's kind of where we're going with that. Also, okay. And then the second discussion talks about your team looks at a lot of visual data, and you want to answer what's a high watermark. How does that work in the concepts of utilization of your system, utilizing your system? And then you have an upper and a lower control limit. What does that mean for system output, and why might that be important to know for this system? All right, we can keep going through this real quick. There's a bunch of definitions and terminology to learn for this week, so that's all there for people that want to go study that. Anything that we talk about this week, you can also put in here. There's no lab assignment. Look, it's a Christmas miracle. But there is the project stuff to work on. Digging deeper, you go spend some time and you read a little bit. Maybe you go get your white belt from Six Sigma. That's a free cert. And if you do that before the end of the course, I'll have some kind of prize or something. I actually had another thing. Anybody that gets their Gremlin certification by the end of this year and tells me about it down in our ProLUG, I'll do something for you guys as well. I don't know what I'm going to do yet, but probably be like a Humble Bundle or, I don't know, like a gift card or something to Amazon. So, all right. So our topics for this week, we're mainly focusing on troubleshooting this week, right? So Sabre, that's what we're doing. We're doing Linux, but we're hitting troubleshooting hard. We're going to talk about incidents versus problems today. We're going to talk about administrative troubleshooting and how that contrasts with engineering troubleshooting. There are two. there are multiple types of troubleshooting, but for us as administrators and engineers and people that are all shades of in between, there is going to be a distinct line between what is administrative and what is engineering troubleshooting. And what I mean by that is administrators are going to have the goal of getting the system back working. They are very rarely going to be deeply involved. They are going to be involved in root cause analysis, but they're very rarely going to care about going back and rebuilding the process. They're just troubleshooting and getting things working again. The problem type things are going to fall more on the engineers. Now, on the other side of that, administrators, when they troubleshoot, they have this one benefit that engineers don't always have. An administrator always knows that the system was working before it broke. What does that mean? That means if you can get it back to its old state, it should be working again, right? I mean, theoretically, you take away all the filled up logs and you take away the too high memory and whatever, and the system goes back to a working state, we hope. So administrators have that. Engineers are often building new things and designing new processes, so they don't always have that benefit of falling back to something or looking at something. Now we have some other things that we're going to do, but we're going to talk about them as we go. But these are the general topics for today, okay? So let's go into troubleshooting concepts. This will be high-level stuff. All troubleshooting, all engineering in general deals with at its core and at its start the scientific method, and that is we observe something, we form a hypotenuse, right? If you guys aren't familiar with it, I forget what movie that is, but he goes, "Is that your hypothesis, sir?" And he goes, "That is exactly my hypotenuse." I forget what it is though, but anyways, formulate your hypothesis and get your reasons for the problem, right? Then we experiment, and your experimentation is going to be somewhat shortened if you're trying to get a system back online. You're not going to have a lot of time to experiment, but you are probably going to test things and validate. I was talking yesterday when we were in the group, and I was saying how I am constantly testing assumptions of things until I can find what the actual problem is in a system. Once we have done our experiments, we come to a conclusion, we analyze our results, we either confirm the hypothesis or we confirm, typically in like research, we confirm the null hypothesis if we can't confirm the hypothesis. You can never refute a hypothesis, really. You can never fully reject something. You can only not accept it, right? That's a little bit out of the scope of this, but that's important to know. And then we iterate. If we don't find the right answer, we just keep looping, right? All right, so that's scientific method. Let's come down here to practical tips. Here's some tips that are just general ideas around this. Is you need to keep good documentation. If you get called out at midnight on a problem, and the problem, let's say the problem isn't even a Linux engineering problem or a Linux administration problem, it's a voice over IP problem, and voice over IP systems just happen to be on your Linux boxes, well, you want to record when you got called out, time bound, right? Like I got called out at 12:01, meaning if they say, why wasn't Linux team doing anything from 10 o'clock until midnight when this happened, you know when you got on the call, you know when you were alerted, you know when the call came to you, when they asked you questions, and maybe it only took your team 15 minutes to fix the problem. So now some other team's going to have to answer to why it didn't get to you in time, right? But the point is, keep your documentation time bound. Very important. When something was observed and by whom. So if I'm looking at something and I find it, if one of my junior engineers or one of the other people in your NOC finds something, note it, alert, and then tell it up to the bridge. Do not trust. I tell people all the time, keep your own documentation. I always keep, when I'm doing stuff like this, I always have a OneNote open, and I am always throwing stuff in here as events occur, as I validate things. System's been up 32 days. If I find out later that the system's only been up for 2 hours, now I got to look. Did somebody on my team reboot it? Did somebody crash the server? Did something happen? Right? There's all these things that can happen, but documentation is really critical. Also, when I document things, I always keep track of what I actually did on the system. So, like, if I were to, if I were over here and I did like an uptime on this box, and I say it's been up for 6 days, I might grab that right there, especially in emails. I always talk about how I want my, at 10:55 a.m. on, 22 December, right? I knew that was up, but I always talk about how my documentation and the things I say as an engineer, I want them to be above reproach. And you say, above reproach, what are you trying to, like, sit on a mountaintop and be like some oracle? No. No. What I mean by above reproach is I don't want anybody to ever be able to come back and say I gave them bad information. So I give them the information and then I prove the things I say. And that's I think that's worked well for me in my career. I think that's valuable to know. You need to have teamwork, practical tips, involve different perspectives and expertise. You may get called out. You will often get called out if you're a Linux engineer and Linux administrator. You will often get called out because people know that you solve problems. This is our blessing and our curse, right? This is the reason the company keeps us around, but it also kind of sucks because you do get called out a lot. I get called out on networking problems. I'm a Linux engineer. But well, I'm high performance compute, so I guess I do kind of have networking. But the point is, bring different people in, make sure that you're listening to them. Don't just point fingers at people and that kind of stuff. Use your tools. I tell you guys all the time, the worst time to try to figure out your tools is when you've been called out. Don't try to figure out your tools then. You want to figure out how to use your tools right now. You want to know how to, like, the first time you open Wireshark should not be when 30 people and a bunch of execs are trying to figure out if two systems are talking. You should know how to figure that out already well before somebody asks you that. And then understand the iterative approach. You're going to have things that you assume to be true and things that you assume that are not true. But as you're figuring things out, you're going to be like, oh no, that system can be pinged. Oh wait, that system is up. The DNS is wrong, right? The DNS is pointing to, I was just talking about this yesterday. I've had it where in an IP reuse situation, something had not released a set of servers. So some process, I believe, had reallocated an IP address that was being used somewhere else. So some people in the network were going to that box. And some people were going to the new box. So when they were on the call troubleshooting, they're like, no, I'm going to that and I'm right in the box. I'm in the right server. It's up. Like, what are you talking about? And then other people who were coming from outside of the organization were being routed via DNS to a different server. One that had been, it was in a decommissioned state getting ready to go away. And it was just, and they looked similar because one was like the older version and the newer. So the point is you're going to be testing things and you're going to be working through things as an engineer. So Atticus over on YouTube side, how's it going? We are just recording information. Now, there's a couple of things you need to know. There's continuous data and discrete data. Discrete data is ordinal, nominal, binary. Ordinal is numerical data, but it has a certain order to it. So, you know, there's a 1 through 5, how good was the call? They love to ask that for like voice over IP calls. 5 would be good, 1 would be bad, and 1, 2, 3, 4, 5 are numbered in like a hierarchy. There's also nominal data, which is just numeric. There's binary data, which is 0, 1, true, false. It is on, it isn't on, right? That's what all these mean. And those can be types of data that you may gather out of an environment, right? But then there's continuous data. Continuous data is existing as like time of day measured in hours or minutes or seconds or microseconds or whatever. Temperature measured in degrees. Those can be different types of degrees, and you want to use like units, right? This is an engineering concept. Always use like units. But I'll tell you right here at the bottom, accuracy, testing and trusting your collection tools and methods is very important. If you're not doing what we call ceteris paribus, which is keeping all other things equal, then, you know, if sometimes you test, if this is, you got a room here and you've got a little circuit, you know, or a little processor sitting in the middle of it, and sometimes when you go in and you test the air up here, and sometimes you actually make contact with the metal and test the heat of the processor chip. Well, those are two completely different types of measurements, but if you're recording them as the same thing, I mean, we might as well, it's called garbage in, garbage out, right? If we're going to put garbage in the system, don't be surprised if you get garbage out of the system. If you take the best methodology on planet Earth and you just feed it bullshit junk, how are you going to be mad when it doesn't give you a good outcome or a good answer, right? All right, so something to think about. So, let's talk about administrative troubleshooting. What are the types of troubleshooting? What are the things that we're doing as administrators on a system? And here's one. This is the 8-dimension problem solving. Maybe you stand up a team. You stand up a bridge call in the middle of the night. Certain levels of incidents, depending on how your organization classifies incidents, say that we will call out everybody. So there's customer-facing downtime. We describe the problem. What is the problem? Is the problem actually that the system is down, or is the problem that customers can't do certain things on the system? Because the system may be up, but a certain component of it might be down. So you need to describe the problem so people aren't just running around. There's a lot of system. Like we have, over time, lots of business processes that are running. We need to describe the problem and scope it down to what is actually happening. We might develop interim containment actions if we know that there are things that are happening. Maybe it's a security incident, we know it's affecting other things, or it's a database and the database is going to shut down if it hits a certain amount of load, so we need to start to offload and maybe do like read-onlys against some of our read-only databases and start to do some stuff, whatever it is, we start to contain the system. Maybe we start to spin up our pilot lit system because we expect like a power outage in this environment or something like that, and we start to turn on our pilot light systems so that they can start to get ready to handle the moving of the data that we can. We define and verify root cause. So if we have the root cause of the system, now we don't spend a lot of time looking for root cause here. This is an interesting one here to have because root cause typically comes later if there's a real problem. What I would say is if we're trying to solve an incident, we're going to figure out what we think is wrong and start applying fixes to that quickly, right? Which is here, verify permanent corrective actions, implement permanent corrective actions. So there's verify your things are going to work and then implement them. And then we try to prevent recurrence, so keep things from happening again. And then again, you can congratulate your team or whatever. This is one way to do problem solving. Let me show you a shorter way that looks very similar. This is the 7 steps for troubleshooting. I learned this in the military. They get shorter than this, but this is the general idea. You're going to identify a problem. You're going to establish your theory of probable causes, or maybe you're going to make a table. You're going to test your theory to determine that the top one is actually the one. Maybe you need to reorder and sort some of the things. You're going to establish your plan for resolving, and then you're going to implement your solution. That's it. Verify functionality, implement preventative measures if you want to, or if you have time, and then document your findings, actions, and outcomes. This is a very common 7-step troubleshooting that's used by administrators and engineers. Military uses this for like live troubleshooting of problems, right? Let me show you another one. This one's only 6 steps. It actually just combines 4, 5, and 6 here, right? So it's identify a problem, establish probable cause, test the theories, establish plan of action, verify your full functionality, and then document your findings. So there are different ways to do this, but this is another way to do troubleshooting. I'm going to tell you the same thing I always tell you guys as engineers and admins. Don't try to learn all of them. Don't be like, okay, I'm going to use the 6, 7, and 8, and I'm going to apply certain rules of each. No. Find the 1 or 2 of these that resonate with you and run with that one. Okay. This is important. All right. So the next one is, this one comes from Microsoft. We're not gonna fault Microsoft. They actually have a pretty good method. It's called React, and it's easy to remember because it's React. We react to a problem, and the first one is you start to research, and then you engage. So you've been alerted to a problem. You start to research what's going on. You engage. Maybe that engagement causes you to come back to research and spin, maybe. But then you engage. You start to adjust the system to get it back the way that it needs to. Then you configure the system to keep this from happening again, and then you take note of what happened. This is a very simple. You could throw this up on a notepad as you were working with a team, and you could say, okay, everybody, figure out what's going on with your systems. Go ahead and get back to us. Let us know if you have any questions about the problem that we've described, and you could be finding out what's going on and asking your questions. And then what do we think we need to change? We don't make any changes to start, but we talk about what we think should be happening. Do we need to restart something? Do we need to reinstall a driver because a new set of drivers come out? I have one here in my home lab here on my system here. Every effing time I go to start my Streamlabs, right, to stream, I get a crash, and then if NVIDIA has updated to a new version of a driver for my video card, I have to go and update that new driver. you say, really? Yeah, it's pretty bad. It's one of the most annoying things around, because it leaves like artifacts up in YouTube that says I don't know. It's a super annoying thing. But anyways, sometimes I have to reinstall drivers is my point there, and that's something that I just have to do every time that comes up. And then we configure to enforce standards and update standards as needed, and then we take note. Now, you might say, well, Scott, what would you do to keep this from happening, this problem that you keep having? Well, what I could do is every time before I start streaming, I could just go check NVIDIA to see if they have new drivers. I think that's a true hassle, but if they have new drivers for my system, yeah, I'd say probably like 90% of the time my my Streamlabs is going to crash. It's like the dumbest thing. But, I mean, I do know how I can prevent it. Then I got to balance if the prevention is worth more than the time to just, fix it the other way. But anyway, so this is the React method. Next one. This one's probably the one that's helped me the most in my career. I call this stepping through the OSI model. And, what's the first rule? If I told you need to step through the OSI model, and you knew like nothing else about what I was talking about, what would be the first thing that you might think you had to do here? If we were talking about stepping through the OSI model. I'll just go ahead and tell you. It would probably be knowing what the OSI model is, right? Maybe even knowing the context of what it is. But the OSI model is a communication model made by the ISO, which is kind of funny. The International Standards Organization runs the OSI. And this model deals with how data moves through our system, through our environments. All data, everything, us here talking, you guys going on and watching your cat videos, pulling stuff down from YouTube or doing whatever, every single one of these comes from this. So stepping through the OSI model is interesting and important. This is one of the things that I show you guys often. If you turn on a machine and you ping another machine here, so I just pinged it, right? Ping is ICMP. Does anybody know what layer of the OSI model ping and ICMP operates at? Does anybody know? So I sent a message to that machine, an ICMP echo. I got back an ICMP reply. This might seem overly simple to some of you, but this is valid for people that have never done it. That's operating at layer 3, right? We're using the IP address to hit it. I didn't use DNS, so I'm not way up here. I used an IP address right here. Now, think about this for a second. If I ping that machine and I got a response back, it might help to see this. This is the flow of data. But if I ping that machine from here, and it went all the way over here at this layer and came back to here, do I need to go check that the physical cables are plugged in on those machines? No. Do I need to check that their wireless cards, if they're using wireless, are connected? No. Do I need to make sure that the machine is turned on? No, because I just pinged it. Do I need to make sure that it's operating on the same layer 2 schema as me, like it's Ethernet 2 frames or whatever? No. Also, it wouldn't matter if they were or not, because whatever they're connected to would determine that. But would I need to make sure that they were connected? Maybe go make sure that they have a good link laid out of the back. Maybe do like an ETH tool like this. Would I have to do like an ETH and make sure that their link was detected? No, I wouldn't have to do any of that stuff. And the reason is because I've gotten the communication to work all the way up here, right? So my point here is, as a systems administrator, systems engineer, as we think through this stuff, the data flow down on one side, they flow across at the physical layer, and they flow back up the other side. The only communications that ever occur, the only communications, guys, that ever occur are between each of these layers, up and down. So if something breaks, you can find it because you understand how they communicate, or over the physical layer. And then between these as they go up, but hold on. Since the packages talk directly across each other, the data flow, the frames, the packets, the segments, the data, since they operate across, you can also tell if something is broken if it gets to here, if the communication is not working between the two. What I mean is, like at the presentation layer, you do 3 things. You encode, you compress, and you can encrypt. Those are the 3 things you can do here. Well, on the far side, when the data have flown back up to here, then you can decompress, decrypt, and decode. Those are the only things that happen at this layer. So thank goodness you took the Network Plus. Yeah, Atticus, networking and Network Plus and Cisco and all these things, they really will help you, because at the end of the day, as a Linux systems administrator or as a Windows administrator or as a, I don't care what you're doing in tech, everything you do touches a network. So being able to troubleshoot how your system is interacting with that network is huge for you to be able to troubleshoot things. So I have greatly benefited in my career as a systems admin and a systems engineer from understanding the OSI model. It's greatly helped me. I think it'll greatly help you too. I have a little network primer on this that's on a different course, but you can also find these slides up in the Discord if you guys want them. All right. So then we get those, all the troubleshooting that we looked at so far, all of these were abstract. They could be applied to anything, right? These didn't require you to know the system you were in. And then down here we get to, you need to be an expert in systems, but you do not need to understand this system. So what I mean by this is a doctor right here. This is how a doctor troubleshoots. A doctor knows a lot about the human body. They know a lot about Linux, let's say, in this case. But they don't know about your version of Linux. They don't know your environment. So a doctor looks at you and they press down on your tongue and they look in your ear and they check your eyes for responsiveness, and they understand symptoms to identify and diagnose a likely cause, and then they try to treat it. So they are experts in systems, human systems in that case of a doctor, but they do not know your system. They're just introduced to your system maybe right then, like in an ER or something. And this is how they troubleshoot things. And this is a method you can use, but again, this requires you to be an expert in Linux systems and networking, as it were, right? So understand symptoms, identify the most likely cause, and then treat it. So this one is a little more complex than the other ones. The other ones are more, any admin can do it. This one is, I'm starting to become like an expert, maybe even a senior level or staff level engineer of some type, and I understand this. Now the next one I'm going to show you is by far the most complex, because it requires an expertise in systems and it requires an expertise in this system. This is the most difficult one to attain, but this one, you'll have a few gems. You can become one of those gems in an organization. This is like real value to the organization, is this person right here. Systems thinking. Systems thinking is the process of analyzing all interdependent components that comprise a system. They know how it's supposed to connect. They know that it is a DNS round robin, comes into one of two load balancers in one of two different regions out in AWS. Those two load balancers have weighted load balancing happening to maybe 30% on this one goes to your data center, 30% go to a set of scalable resources inside of the cloud, and then the last 40%, right, because that was already 60, the last 40% maybe go to like a Lambda function, and that Lambda function sends off to an SQSQ. And the point is, they can close their eyes and they could draw this whole system out for you, and then they can see where something's not working based on the troubleshooting and reading the logs and those kind of things, right? But they're looking at the holistic view of the system. Now, when I just described some of that, some of you were thinking, yeah, this person's probably spent some time. They were maybe even the one who built it. Yes, systems thinking, this idea is going to be some of the most complex and high level that you're going to run into, but you really want to engage. You want to be one of these people, first off, in your organization. You want to know your environment, but two, you want to be the one, you want to understand the system well enough for that. Anyway, so what are the systems or devices between this device? So, when I was just talking about that, where the load balancer is pointing back to a scalable set of EC2 instances, maybe, you know that there is a TLS termination that's happening at your load balancer back to those devices. So I don't know, maybe there, as you go to look at it, there was an exhaustion of IPs within the subnet that you had, and you couldn't scale up to any more EC2 instances. But how the hell would you ever know that? You might find, by looking at the system that the load balancer couldn't communicate anymore and there were no more open connections. But if you didn't understand where they were sitting and if you didn't understand their regions and all that stuff, you might never be able to go troubleshoot that other part. So anyways, my point is systems thinking requires by far the most expertise in the system, in both the areas of knowing systems and knowing this system. So what other devices are attempting to communicate with the same system at the same time? Is their communication still working? Are there dedicated resources? Are we coming in on multiple different VLANs and we have traffic shaping and traffic policing, which are two different ways of dealing with extra traffic in a network? What's changed in the environment and in which system operates? Like going and looking back at change management to find that somebody made a firewall change today. And then has the system been physically moved recently? That's a question that's interesting because you say physically moved, right? But have any of you here ever worked with virtual machines? I bet a bunch of you have worked with virtual machines, right? Have any of you ever worked with virtual machines in an enterprise? Also, you raise your hand. Have any of you ever had a virtual machine moved by, what is it in VMware? It's like DRM or something, DRM, whatever that tool is that moves, it does your vMotions. But have you ever had a virtual machine move to an environment where a VLAN doesn't exist on that host that did exist on the other host? Now you do. And now you think, wait a minute, this system was working fucking fine and peachy over here, but it was virtually moved to a new ESXi host that maybe doesn't have something that had been changed in a change record on an older one, and a new build doesn't get it because maybe your VMware team or your ESXi guys, which again might be your Linux or your Windows engineers or even storage engineers, maybe they just didn't move it into their baseline, so now that's something that's like a one-off that needs to be fixed over there, but nobody was ever going to catch it. There's too many moving parts, guys. There's a lot of moving parts, right? And this is hard to do, but this is how we troubleshoot things, right? We need to understand our systems. All right. So here's another one. This is a kind of high level, like a framework, and you can go study up on Kepner-Trago if you want. But they do situation analysis, figure out what's going on, problem analysis, what is not working the way that we expect to. Sometimes, you get this. People will call you up and say, hey, that Linux server's down. And you go to it, and the Linux server's got an uptime of like 3 months. So you're like, it's not that. The server's up. And they go, oh, well, what we meant was it's not responding on the API anymore. And you're like, all right, well, that is a different thing, and I'm glad that you guys clarified that. Okay, then maybe a software service isn't running. Maybe something changed in your environment. Kiwi Bytes, you said, what's an ESXi? ESXi is the hypervisor platform. It's a type 1 hypervisor that VMware uses. I don't know if they even use ESXi anymore, if it's just ESX now. I forget which one went away back in the early 2010, 2012 timeframe. I think it's ESXi is the one that's still around. But that's what VMware uses, their hypervisor platform. So anyways, all right. So then we do a decision analysis, and then we have a potential problem. We analyze it, and then we figure out how to solve it. Okay, so that is our administrative troubleshooting. There's a lot of things you have to think about as an admin, but I'm going to tell you guys this, like I said earlier, you don't have to be an expert in all of them. Find one that works well for you. If it's this React method, use the React method. It does come from Microsoft, but we're not going to fault it because the method itself is good, right? You don't have to say I'm using Microsoft's React method. It's just the React method. Stepping through the OSI model has probably been the most useful for me in my career. Understanding how the data are flowing is important. All right, so let's go down to engineering troubleshooting. So how do engineers do things different? Their engineers are going to look at problems before they happen. So we're going to look at that a little bit. They're going to look at problems that are happening in an environment and deviations from system outputs that we expect from processes. And then they're also going to do post-mortems, like after-action reviews of things, right? And how to make things better. So let's look first at failure modes and effects analysis. So FMEA tries to do these three things. It tries to identify, assess, and then prioritize problems that may come up. One of the nice things about failure modes and effects analysis is, let's say you were getting asked to build a brand new environment for a company. Well, if you've built environments for companies before. You can do a failure modes and effects analysis before you ever even deploy it. You can look at what problems might happen. You can assess them and give them a priority, or you can prioritize them and figure out what the priority of fixing them would be. All right, so let's go look at failure modes and effects analysis. So it comes from an old government technique. The military, the government uses this. You'll run into this if you do any government contracting for sure. But it talks about what could go wrong, what impact might it have, what's its likelihood of occurrence, and then what is our ability to detect and react to it. So I'm going to show you guys an example of walking through this. So real quick, here's some preparation. Make sure you know your system functions. You need to understand what you're looking at. And then you decide how much you want to decompose the system down to think about the system or the subsystem or the assembly or the part or the single part. What do you want to look at as a system? What I'm going to show you is, well, let's pop to it. I'm going to show you one that I did. I actually did this. This comes from a company I worked for. And what was happening was we had about 200 dev teams. And these developer teams ranged from like 2 engineers up to like maybe 40 engineers, depending on how big the team was. Some of them, there was some overlap between where the engineers were. But basically these dev teams could come and they could like push a little button on a thing called VRA, which was some vRealize something, vRealize automation or something, but it's like a dashboard. And they would say, I want 2 servers. And I want those servers to have like these extra disks for applications, and I want them to be in this environment down in dev. And they would basically, it was like putting a little quarter in a gumball machine and going like this, and the little gumball would come down and they would have their little servers. That's how our system worked. It would produce a server for our users. It would send them an email and say, this is your server. It's in this environment. It's going to be good for 60 days, right? Because that's what most of our dev servers were. If you need it for longer than that, or you need to get your data off it, here's where your home directories are going to be. And we had all these things that would come in the email so that they knew how to use their server, but they would immediately have access to their server just from one button push, right? This was our goal. We had that working, but there were problems. Things came up. So I rounded up possible failures on my side of things to figure out how we could make sure that the little gumball going down the little gumball machine didn't break at different areas. And these were 4 failure modes that I found often, or to be the most, let's say. The ones that, I had other ones in here, but this is my cut down list. So one failure mode was the initial image was unavailable. We booted everything off of a golden image. My junior engineers typically would go every 3 months, and they would update an image to have the most, updated kernel and all these other things. And they would be at the same kernel version as any other thing that was in the prod environment, right? Because you develop towards prod, so you want your stuff to be similar. That's actually one of the, if you ever do 12-factor stuff, if you ever study 12-factor, dev and prod should be mirrors of each other. The only difference between development and prod should be development is probably going to be a little smaller because you can't afford to run 2 prods, right? Typically. But anyways, the point is they're the same. So initial image would be unavailable. So the image that my junior engineers had made and put up into a VMware, they have these little things called like libraries or something, couldn't be reached. And the cause would be maybe backend storage from one of those ESXi, virtual hosts wasn't able to access it. I don't know, maybe it's a transient problem, maybe just a server came up and didn't get the connection and never went back and reconnected. Who knows? But our current control to solve that was just to be monitoring vSphere systems and make sure that they could see all of our libraries where our server repos were. So that was our failure mode, the cause, and the current controls. Now, next one, once the server came up, there was a tool called vRealize Orchestrator. This is like an automation tool that exists inside of the VMware side of things. I don't think a lot of people use it. And with VMware kind of going out in the industry because of what Broadcom did to them, I don't expect a lot of people to ever use this. But this VRO would connect in and it would make calls over to our Ansible automation platform, which used to be called Ansible Tower. And it would kick off jobs against the servers to do all kinds of personalizations. In fact, if the machine was built here, then it would come down here and it would have a bunch of disks, and the virtualization, the VRO, depending on how the person asked for the server, Remember I said earlier that they could have like multiple disks? Well, we allowed them to add multiple 600 gig disks. That was the size of the thing that we allowed them to do, and I think they could put up to like 5. Well, what would happen is they would say, well, we want that to be in opt, whatever our tool is. And my Ansible would go, and it would take that name that they had given it, and they would take those disks, and it would do all the logical volume management stuff, right? Super easy to do in Ansible. There's modules for it. And it would carve those disks. It would put those up into physical volumes, volume groups, and then carve them down into logical volumes to be added into that directory so that they would have those disks and they would have a place to go do their, dumping of data for whatever their application was, right? But that would break sometimes. And the reason it would break is because VRO had a service account in our environment, and that service account would cause that service account would have to change its password every like 60 or 90 days. I forget what our standard was. So maybe the credentials were out of date. And how did we fix that? We had a daily build process. All right, I'm not going to bore you guys with all of these, but the point is, because I had experience with the systems, and this is a qualitative assessment of the system. So we went and rounded everything up. Now we got to put numbers to it. And the numbers of failure modes and effects analysis there's always 3 numbers. There's the severity between 1 and 10, the probability between 1 and 10, and the detection between 1 and 10. Now, if you're going to multiply 1, 1, 1, the lowest number you could have is 1. And if you're going to multiply 10, 10, 10, you're going to get the number 1,000. So, your risk priority number exists as a number between 1 and 1,000 to organize the risks associated with any of those problems happening. So, customer impact, the most impactful one was these final build checks failing. The likelihood of it happening was kind of high, but we had a pretty good detect and react on it. So it only got a 56 score. Go make sure my numbers are right there, right? And then you go up here. This one is 5, 5, and 9. We did not have a good way to determine and detect this, so this caused itself to have a much higher risk priority number. I would say all of these are pretty low, though, in the big scheme of things. But if you were to say, hey, Scott, where are you going to send the junior engineers to go try to fix stuff? I'd go send them to try to figure out that the agent register. I said Avamar. That was one of our agents. But agent register for server fails. That would be the 225. And then where are you going to spend your time? I'd probably go look at the final build checks fail and see if I could write that a little better or make that work better, right? But the point is, you could start to figure out and triage. This is a triage methodology of what's the most important thing in your environment. This is more, again, this is more engineering. This is more preemptive. This is not an admin type task. The admin stuff earlier was like, there's a wheel off the vehicle. We need to get the vehicle back working. This is, we're designing the vehicle. We're designing the environment to work better, right? So anyways, that's how failure modes and effects. All right. Now there's root cause analysis. You're going to be called on to do these a lot as live systems break and as different things happen. So I'm going to give you 3 methodologies that we're going to look at. We'll look at the 5 whys, which you just start asking why. The major detractors from 5 whys methods talk about, well, if you get to the last why and you're still only at a symptom, you haven't really found out what was wrong with that's fine. You can add more whys, guys. Another one is fishbone. Fishbone is to put in all the potential inputs to a system and see what's causing the error. So we're going to look at that. And then we'll do fault tree analysis, which is, fault tree analysis is fun because it talks about, what's the desired state, and then how did we get to the undesired state by looking at like Boolean logic. And I think that fault tree analysis is very useful. The ones I've seen used by far the most, these are grouped in the order of how I've seen them used in the industry. We normally do 5 whys. Just we hammer these out real quick. Fishbones, I've drawn up fishbones before because sometimes you need to just figure out what input is causing the system to break. What is the thing that's not working here as engineers? All right. So here's the 5 whys. This is a little worksheet. You can go grab any number of them out there, but you define some abnormal condition, and then you walk through. Now, when we did this yesterday as a group, we actually made, let's see if I can pull this up real quick from our Where's our Discord at? Hold on. In our Discord, we actually made a, let's see if the notes look good still. Yeah, so here are the notes that we were doing yesterday. This is in the Discord too if anybody wants it. But some of you guys were taking notes, so you can grab the notes. And then for mine, this was my Scott's notes, stay out. And we just started to walk through and we said, the server rebooted. Well, why did the server reboot? Well, was the command given to reboot the server or did the server crash? If the server crashed, why did the server crash? Now we got to go look at some logs. And then we find out that the server crashed because somebody had tried to update it. Why was it being updated? Why was the server in production being updated? And then you say, well, was that process allowed to run? Did somebody accidentally kick it off? This and this and this. And then we find out, oh, well, the reason that the process was allowed to run was because we hadn't put like some protections on what we call sometimes guardrails on the ability to run that process in normal business hours. That process should only ever be run at night in a change window that's defined by the company. So we find out that the server was rebooted because we did not put guardrails in place, and that caused all these things to happen for the server to crash. So the server would have never crashed if it wasn't updated. Would have never updated if we had not allowed that process to be kicked off incorrectly by somebody. So then we fix it, right? We fix it again down there. So anyways, this was kind of an idea. And you can ask with the worksheets, 5 whys. Again, some people are like, oh, I don't like that. Well, you know, there's other methods to troubleshoot stuff. I just think this is an easy one that works. And it typically gets you down to a root cause. So here's a fishbone. Fishbones almost always have material, measurement, machine, method, environment, and people. There's almost always 6 inputs. Could you add more? Yes. Could you make each of these longer and add more? Yes. But material, you're putting garbage into the system. Poor storage conditions. You've got a whole bunch of cloth, but the cloth has been stored improperly, so it's really bad as you go put it into your system. Maybe your measurement's wrong. Somebody put the wrong type of server. I've had this happen before. Where we're like, hey, go build a whole bunch of Rel 8 systems, but somebody uses the wrong documentation and builds a bunch of Rel 7 ones, and you're like, tear it down, start over, right? But the point is, you will figure out, if you do this, what caused a system to be broken as it came as an output. All right. Fault tree analysis uses standard gate logic and or. These are the same types of gate logic you're going to find in most engineering drawings, right? You got fault events, basic events, undeveloped events, and normal events. And your plant burns down. And was it combustibles or was it the fire out of control? It was both of these things. But the ignition was either smoking or sparks or a short. And we don't know, but there's a probability of those things occurring. And we can go look at those things, right? It's actually interesting when we don't have to dig too much into that, but you can calculate these multiple ways and you can go and play with. They probably even have, I bet they even have a generator out there that'll generate these for you. I didn't look into that too much, but all right. This next one comes from Six Sigma, which is the plan, do, check, act. Plan, identify a problem and plan for change. Do, implement the change on a small scale. Check, measure the results, see if they led to an improvement. And then act, successfully implement it. Now, some of you that are familiar with like one-box methodologies or canary deployments or those kind of things, this looks a lot like a canary deployment. This is the way that we update and keep our systems moving forward as engineers, right? How do we take a version of software and deploy to a new version without affecting all of our customers? Something like this, plan, do, check, act. This directly comes from Six Sigma. This is directly one of Deming's principles. Edwards Deming, but this is a plan, do, check, act, and then there's other versions of it, but PDCA is a very common one. You also have, as you start to break down and look at processes, you have these things called the SIPOC diagrams, and that's supplier inputs, process outputs, and customers. Now, as software engineers, most of you understand input, process, output, or as Linux engineers or as systems guys, input, process, output. That's what we do. But we were talking about this, how one of your inputs to a system may be to go call over to an API and get some data. And that API becomes a supplier, and maybe that supplier is only up. Maybe you get a 500 error 13% of the time. So 87% of the time you get no problems, but your inputs coming off of that supplier are bad 13% of the time. Well, you need to determine, is that time bound? Is that, could I just do 3 requests over time and take the most current one that comes back? Like, you're going to have to figure out how to make that always be a good input to your system. Process outputs. And then your customers are the people who are going to visualize and see whatever the output of process. Some outputs just feed into the inputs of another process. You know, if you talk about like Node Exporter just gets scraped to Prometheus, and nobody else ever sees that. But from Prometheus, sometimes things are visualized, and sometimes a Grafana process comes along and takes from Prometheus and then creates an output that customers can see, right? So there's like, so if any part of any one of those broke, I could have each of those processes broken down. Now, the reason processes are so important is something else that Deming said, and this is very important as an engineer, and I'll go ahead and say it now and everybody will forget it, but this is one of the most important things I've ever learned as an engineer, and it's that, yeah, if you can't break everything that you do down into a process, you don't know what you're doing. So if you've got, you know, if you've got no server and then you've got a server here, and I say, okay, break that process down for me, and you go, well, we push a button, and well, we have a server. I'd be like, I need to talk to somebody else. That's what I'd probably say. But the point is, do you understand that you, at least in that case, where you say, I push a button and something happens, you don't understand what's going on? Do you? I mean, I'm not trying to insult anybody. I'm just saying you don't. So if you can't break everything that you do down into a process, you don't know what you're doing. I'm not saying you didn't delegate it to somebody else. I'm just saying, if I'm an engineer in here to help you fix your processes, and you've got me talking to a VP, and that VP just says, well, I come in the morning, the coffee's on my desk. And I'm like, yeah, okay, well, who makes the coffee? And they're like, I don't know. And I'm like, well, if I'm going to get to the solution of why you have cold coffee, I need to see the process. Does that kind of make sense? And I'm not trying to oversimplify things. I'm just saying, you need to, if you want to be a person who improves processes and build things and troubleshoots and that kind of stuff, you got to get down in the weeds of the processes, not just the output customers at the end, right? All right, anyways, SIPOC diagrams. All right, no labs for this week. I went easy on you guys. It's Christmas miracle. So you got a lot of troubleshooting labs. We're going to have a pretty fun troubleshooting lab next week. I got a plan. I need to see if I can get some guest speakers to come in on that one. So it'll be good. Yep. All right, so questions. If you have questions, hit me up in the Discord. Message me. Do whatever for that. Okay, so this was our recording. What did it take? It took about 53 minutes, so I added a little bit to it. But this was our Unit 15. Everything that you guys might want, if you were to say, hey, what is this course? Everything you could possibly want around it is down in our Discord. So you go in our Discord, you go to the ProLUG projects. Here's the last 15 weeks of this course. There's 1 week left, right? 1 week left of the course. The course is going to run until January 19th. And people that finish the course are going to get a little certificate, like a little ProLUG certificate that's real nice. We're only going to give them out the one time. There's never going to be a chance to get this particular one ever again. There will be another one later for people that want to do the course later and stuff, but the original one of the original people that went through the course will only do the one time. So there's a lot of work. Right now, for somebody that was trying to catch up, you'd probably have about 120 to 130 hours worth of work right now to catch up. So, oh, you got to go do the work, Glausen. You got to do the work. The first part of the work is going and finding ProLUG projects and doing the work. Right? That's the first part of the work. Look at all this. There's all work in here. Lots of discussions to answer, a lot of labs. I have all kinds of assignments, projects. There's a project to do. Project's going to be due by the 19th. It starts all back up here. All right, but anyways, that's in the Discord for people that want it. Other than that, let's go ahead and I'll stop the stream here. I'll probably hop back on a little later, and we'll just do some general, maybe some general networking stuff and Linux stuff like we'd been doing. But let's I'll go ahead and take a break for a little bit. I appreciate you guys all come by. Again, just one more of these courses, and then we'll be all done with them. So if you guys want the Discord link, here's the Discord link. That's free. People can hang out down there all they want. But we will probably pick it up later, just doing some basic Linux stuff. So, all right. Take care, everyone. I will